How many ordered pairs of positive integers a, b, with a is less than or equal to 100 and b is less than or equal to 10, exist such that neither the numerator nor denominator of the below fraction, when completely simplified, i.e. the numerator and denominator are relatively prime, are divisible by 5. 4 to the b plus 121 to the b over 2 to the a minus 3 to the b. If neither the numerator nor denominator of the following fraction are divisible by 5, then either both 4 to the b plus 121 to the b and 2 to the a minus 3 to the b are themselves not divisible by 5, or they both contain the same number of factors of 5. So when you drain the factors of 5 out, you get both the numerator and denominator not divisible by 5. For example, you can do 375 over 875, which is equal to 3 times 5 cubed over 7 times 5 cubed. These numerator and denominator themselves are divisible by 5, but they contain the same number of factors of 5. So when you drain them out, it becomes 3 over 7, neither of which is divisible by 5. So both the numerator and denominator of this fraction have the same number of factors of 5. It could be 0, 1, 2, 3, anything. We just have to find when both the numerator and denominator, 4 to the b plus 121 to the b, and 2 to the a minus 3 to the b, have the same number of factors of 5. In other words, the largest power of 5 that divides them is the same. The searching space we're given for b is relatively simple in itself, as b is less than or equal to 10. And we want to know whether the numerator and denominator are divisible by 5. So we use mod 5. First, we use it on the numerator, 4 to the b plus 121 to the b. And note that 4 to the b can only have two values, mod 5. It can either be 4 if b is odd, like 4 to the 1, and 4 cubed end in 4, meaning they're 4 mod 5. Or they can end in 6 if b is even, like 4 squared and 4 to the 4th, 16 and 256. In that case, they're 1 mod 5. So if b is odd, then 4 to the b plus 121 to the b, and 121 to the b can only take one value mod 5. It's always congruent to 1 mod 5. So if b is odd, then 4 to the b plus 121 to the b is congruent to 4 plus 1, which is congruent to 5 or 0 mod 5. So in that case, it is divisible by 5. Otherwise, 4 to the b plus 121 to the b is congruent to 6 or 1. That's what 4 to the b is congruent to mod 5 if b is even, plus also 1. 121 to the b is always congruent to 1 mod 5, and 1 plus 1 is congruent to 2 mod 5. So if b is even, then the numerator is not divisible by 5, otherwise it is. Let's start with the even case. If b is even, then we only require that the denominator not be divisible by 5. So 2 to the a minus 3 to the b is not congruent to 0 mod 5. And so 2 to the a is not congruent to 3 to the b mod 5. This means 2 to the a, 3 to the b is congruent to 8 to the b mod 5, which is 2 cubed to the b mod 5. It would be nice. So 2 to the a is not congruent to 8 to the b mod 5, which is equal to 2 cubed to the b mod 5. So a and 3b, when 2 is raised to the numbers a and 3b, they don't give the same result in mod 5. And the powers of 2 mod 5 cycle in groups of 4. You can have 2, 4, then 8 is congruent to 3, and then 16 is congruent to 1, and it repeats again. So it cycles in groups of 4, and thus we only require that a is not congruent to 3b mod 4, if b is even. So 1/4 of the time, with a is less than or equal to 100, a is not going to work. The other 3/4 of the time, it is. So that's 75 for each even number b. So 75 times 5 is equal to 375. But we're not done. The other case we have here is if b is odd, in which case 4 to the b plus 121 to the b is a multiple of 5, but it's also a multiple of 125. And it's well known that p plus q divides p to the n plus q to the n for all positive integers p and q if n is odd. So in this case, 4 plus 121, which is 125. If b is odd, 125 would divide 4 to the b plus 121 to the b. So then, what we're looking for is that the denominator is also a multiple of 125. That's the only way we can drain all the factors of 5 out to get a fraction where neither the numerator nor denominator are divisible by 5. So we want 125 divides 2 to the a minus 3 to the b, or written in modular arithmetic terms, 2 to the a is congruent to 3 to the b mod 125. And it would be nice if the second base was also a power of 2, as before. So why not just turn that 3 into a 128, which is 2 to the 7th? So then 2 to the a is congruent to 128 to the b mod 125, same thing. 3 to the b and 128 to the b are the same thing in mod 125. And this means that 2 to the a is congruent to 2 to the power of 7b mod 125. And now the first value of a greater than 0, for which 2 to the a is congruent to 1 mod 125, is 100. You should know this since it's just number of positive integers less than or equal to 125 that are relatively prime to 125. So all numbers up to 125 except the multiples of 5, there's a total of 100 of them. We call this the order of 2 mod 125. And it only works when 2 and 125 are relatively prime, which they are. So this is equivalent to saying that a is congruent to 7b mod 100. And since b is less than or equal to 10, we must have a equals 7b, because a is not going above 100 and b is not going above 10. So a equals 7b and b is odd. So we can have ab equals 7, 1. And we can also have 21, 3, ... up to 63, 9. That's everything that works for this case. There's a total of 5 of these. And when we combine these 5 with the 375 we got from our previous solution, where b was even, we get 380. Answer choice D. Thank you for watching my YouTube video, and please follow my channel if you would like to see more videos.